All right, welcome back, everyone. Today we're going to be discussing a very important topic in science. It's going to be Notes 3, Measurements and Conversions. We're going to be introducing, for many of you for the first time, the metric system. We're going to go really in depth with that and what exactly that is. It's a pretty important way of measuring things throughout the entire world. There's only 3 countries, including the United States, that don't use the metric system. So it's a very important concept to kind of understand a new way of measuring things for a lot of us. There are some of you that probably have heard or even worked with the metric system before. So for those of you that have experience, you're going to be kind of reviewing it today. And let's go ahead and just jump right into it. The notes for this section of notes can be found right here in Canvas, right there. Notes 3, Measurements and Conversions. This is going to be the video that you're watching right now, the Notes 3 lecture. There's going to be an additional video on dimensional analysis, which I'm going to introduce in this video. And we're going to kind of get some extra practice with that. And once we get that extra practice, we're going to work on the practice problems. And this is the solution video to those practice problems where I walk through the practice problems. So without further ado, let's go ahead and jump right into Notes 3, Measurements and Conversions. So to start off our lesson on measurements and conversions, we first have to understand that in science, there's a standard base unit for pretty much every single type of measurement that you want to make. And we're going to cover that right now in this first slide called the SI base unit. So we're going to learn what those are. SI stands for Système International, and it's a French term. And basically the way it arose is that a long time ago, back when scientists were doing experiments, whatever country they were in and whatever unit that country worked with, like let's say you're in England and you're measuring length, you might have been measuring length in feet or yards. But if you were in France, which is not too far away from England, you probably would have been using the meter. And so this was actually really confusing when scientists wanted to share data a long time ago, and they would spend a long time sharing their data from one country to another, because best way to travel back then was probably by boat overseas or by carriage with a horse. So when they had to share data with other scientists, it was very time consuming having to convert from one unit to another. And so a long time ago, back in 1875, there was this convention called the General Conference on Weights and Measures. And basically what happened was a whole bunch of countries got together and agreed in Paris that we need to set up a general set of measurements that all scientists use across the world, so that it's really easy to convert from, or not having to convert from one measurement to another, so that we are all on the same page. We can just take a look at the numbers and we all know what that means. And back then, I believe there were 17 countries that signed and agreed to it, and now there are many more, and these are the countries that have agreed to this General Conference of Weights and Measures. And what day they have joined. So you can see some of them are actually pretty recent, like for instance Saudi Arabia is pretty recent in 2011, United Arab Emirates as well 2015, that's pretty recent, Ecuador in 2019. The United States joined this general conference back in 1878, so pretty early on. And so now these are all of the countries that have agreed to the SI standard unit of measurement. So all the scientists in these nations agree that we're all going to use the exact same unit of measurement for what type of measurements they are going to be doing. So going back to the PowerPoint here, these are just a couple of examples of things you might be measuring as a scientist and the unit that you have to be using if you're part of that conference, if you're part of the General Conference of Weights and Measures. So the SI units, again, Système International base units. So for instance, if you're trying to measure length, here in the United States, typically if you want to measure length, depending on how far you want to be measuring, you could be measuring in inches, feet, yards, and even miles. But in the science community, the base unit is going to be the meter. Okay, so there's our first base unit, the meter. And the abbreviation for meter is just the letter M, lowercase m. Pretty simple. If I want to be measuring mass, which is not really weight, but it's kind of related to weight, I'm going to be using the kilogram. In the United States, we might be using pounds, but the kilogram is the accepted unit across the world for measuring mass, and that's abbreviated with a kg. Time, of course, pretty much the entire world uses the same interval for time. We're going to be measuring time in seconds, which is abbreviated S. Temperature is kind of a funny one. Some nations across the world use Fahrenheit, like us. Some use Celsius, but in the science community, there's actually another form of temperature called Kelvin. Kelvin's a little bit different because it starts at 0. So there is a limit to like how cold you can get, and Kelvin goes down to what's called absolute 0, and that is the coldest temperature that can possibly exist. So it starts there, and that's 0. There's no such thing as negative Kelvin, and then it goes up. So it's an interesting form of measuring temperature, and it's very closely related to Celsius because you can easily convert. Later on in physics, you'll learn about electric current measured in ampere or amps. That's next semester. Probably your junior year, you'll measure something called moles, and that's the amount of a substance when in regards to how many atoms you have in a sample. That's a funny term, is a mole. And then luminosity, which we won't really talk about this year, is how bright something is, like how bright a candle is, or a light bulb, or even like a glowing metal, like how bright is it. So that's measured in candelas. All right, so let's go ahead and move forward here. Again, one at a time, just kind of breezing through these. Length, it measures the size of an object. In English units, imperial units, that is going to be measured in feet, inches, yards, and miles. And you want to make sure that you're picking the right one, obviously, when you're describing something. Like when you're asked how far is it from here to, let's say, St. Paul, you wouldn't say, it's 30,000 feet or whatever. I don't know how many feet it is exactly, but you would measure it in miles, and you can say, oh yeah, it's about 5 or 6 miles from where I am right now. So this is something to consider. Always make sure that you're picking the right unit. In the SI unit, there are meters, which is, if you're not familiar with a meter, it's approximately just slightly over 3 feet. 3 feet is 36 inches, and a meter is like just over 39 inches, so it's a little bit longer than a yard. Okay? There are smaller conversions to that. Like, you wouldn't describe how far it is from one city to another in meters. You might use something called kilometers, which is related to the meters. And we'll get to that in a minute. Like, how do you convert from like 1 meter, which is about 3 feet, to kilometers? All right? So here's like a picture of a ruler, for instance. An inch is right here. An inch is about 2.5 centimeters. So a centimeter is a smaller version of a meter. There's 100 centimeters in a meter. So centi, if you think about how many cents there are in a dollar, there's 100 cents in a dollar. How many years are there in a century? There's 100 years in a century. Or how many legs does a centipede have? Well, about 100 legs on a centipede. So cent, the prefix cent right there, means 100. So in 1 meter, which is again about, I can't really show you on the screen, but it's about 3 feet or so, there's 100 of these small things, which are called centimeter. And a centimeter is about the width of your fingers. So if you take a look at your finger and how wide that is, that's about 1 centimeter. And if you stack 100 of those, that's about 1 meter. All right? Next up is mass, and mass is just measuring amount of matter an object contains. In the English imperial unit, we have a lot of different units that we use. Pounds and ounces are going to be the most common thing that we use right now. So when we're measuring weight in the US, pounds and ounces. All right? In the SI unit, throughout the science community, it's going to be the kilograms, and a kilogram is going to be about 2.2 pounds or so. So it's heavier than a pound. We also use grams in the SI unit, and a gram is really light. A gram is like approximately the weight of 1 paperclip. So if you took 1,000 paper clips, that would give us 1 kilogram. So here's the conversion for that. 1 kilogram is equal to 1,000 grams. And again, a gram is really light. If you took 1,000 of those paper clips, each one weighing a gram, that would equal 1 kilogram. And a kilogram, to kind of give you an idea of how much that weighs, if you took like a really big water bottle, like let's say like a blender bottle, and you filled that all the way with water to the top, that's about a kilogram. So that's how much that weighs, about 2.2 pounds or so. All right, so you can see here, here's another conversion. 1 pound is equal to 0.45 kilograms, or 453.59 grams. All right. This instrument right here, before I move on, is called a triple beam scale, and this is what you'll use later on throughout the year to measure mass of an object. You put your object here on top of the scale platform, and then on the stage, and then you have this line that goes up and down, and that you try to match it up with this line. And you do that by sliding around these weights on these beams over here. So actually, let's take a look at an example of how you would read that. So let's say you put your object on the scale and then you slide around these weights to make sure that the line matches up. The way you would do that is always start with the biggest weight first. And I like this image because you have to kind of think about, okay, which is the biggest weight? It's not necessarily going to be in order from back to front or front to back. In this case, on this scale, the biggest weight is going to be in the middle, right? So let's say I have an object and I put it on the scale and I slide over that big weight, and I'm going to slide it over until it gets to the 400 mark right here. And when it goes to the 400 mark, the needle dips down and goes below the line. But if I go to 300, it goes above it. So what that means is that I know that my weight is somewhere between 300 and 400. So what I'm going to do is I'm going to leave that big weight at 300 and then move on to the next biggest weight. In this case, the next biggest weight is the one on top, and I'm going to keep on sliding it over until, again, the needle falls down. So when it falls down, let's say I get to 80, and then the needle falls down, and then when I put it back at 70, it kind of rises back up and kind of goes in between 70 and 80. And then I'm going to move on to the next biggest weight. In this case, it's the last one right here. And this one you kind of want to be careful on because it is the last weight that you're going to be sliding. You just kind of tap it a little bit more closer to the edge until finally that needle kind of levels out. And I'm going to go back to the previous slide here. And you can kind of see here there's going to be a line right there on the scale, and there's going to be a line right here as well. And you want those two lines to kind of meet up right there. And when it's perfect, it's going to be the correct mass, and you know that you've gotten the correct mass. So if we take a look at this and we got that line to match up, how would you go about reading what the mass is? Well, it's pretty simple. All you have to do is add up all the numbers that you got for the scale. So we have 70 and 300, and then what looks like to be somewhere between 3 and 4. So I know it's 373, but I can actually be more specific. And so when I'm looking at this, it's going to be 373.1, 2, and somewhere between 3 and 4. So I'm going to say 0.35, 373.35 grams. Okay? And so that's how you would use a triple beam scale. Our next unit of measurement is going to be temperature, and temperature is kind of a funny measurement because when we think of temperature, we're probably describing how warm or cold something is, and that's kind of true, but it's actually not a real representation of what temperature is. Temperature is a measurement of the kinetic energy of molecules. How much energy do the molecules have? And the reason why I say that is because temperature can be kind of, you can be deceived by it. Let's say you were outside in the cold and winter and you didn't have any gloves on and your hands get really cold and you were shoveling snow for a while, and then you come in and you decide you need to wash your hands and you turn on the tap with lukewarm water, and when you put your hands in, which have been really cold for a while, in that lukewarm water, you might perceive it to be really, really hot even though it's not. There's just a big difference in temperature. So the way we perceive it can be kind of tricky. Similarly, if you were used to that lukewarm water, you could actually bump that temperature up and wash your hands with pretty warm water. So we measure temperature to describe, okay, what's the energy of the molecules in this substance. The SI unit for temperature is Kelvin, again, so we talked about that a little very briefly. It's labeled K. Just a quick note here, it is not degrees Kelvin, it's just Kelvin. So you wouldn't say, oh, it's 373 degrees Kelvin in boiling water. You would just say it's 373 Kelvin. Other units of measurement, we've got degrees Fahrenheit, which is something that we're used to here in the United States, and degrees Celsius, which is a unit of temperature, again, that a lot of people use across the world to describe how hot or cold something is. All right, so how do we convert from, let's say, Celsius, which is something a lot of people use in the world, to Kelvin? It's actually pretty easy. Going from Celsius to Kelvin, there's a simple formula, and this might look kind of tricky, but it's once we describe what we're talking about, it's really easy. This T with the K in the parentheses, this means temperature Kelvin, so whatever the temperature is in Kelvin is equal to whatever the temperature of Celsius it is, plus 273. That's all you have to do is add the number 273 to whatever temperature in Celsius you have, and then you have Kelvin. So for instance, Celsius at the freezing point of water that we have here is 0 degrees Celsius. That is equal to 273 Kelvin. All right, and boiling water, which is 100 degrees Celsius, is 373 Kelvin, because all we had to do is add 273. One quick note, Celsius was developed around the idea of water. Water is such a crucial molecule in chemistry and to life that Celsius was kind of developed around that water freezes at 0 and boils at 100, and then we kind of just, take measurements in between to describe degrees Celsius. All right. In this class, however, we won't be using Kelvin that often. If we are describing any temperature change, which won't be too often, we will most likely use Celsius. I might throw in a problem here or there to kind of discuss, okay, we have Celsius. Let's see if you remember how to convert that to Kelvin. All right, our next unit of measurement is volume, and volume is the amount of space an object occupies. All right, and there's a lot of different ways we can take volume. The SI unit is the cubic meter. The other unit that we could use is called the cubic centimeter, and the reason why we also have that is because we're not always measuring very large things. Sometimes we're measuring very small things or small amounts, and a cubic meter is actually really big. If we wanted to talk about how much air there is in a room, then cubic meter might make sense. But if we want to talk about, let's say we found a rock and we want to measure how much volume this rock is, I wouldn't use cubic meters, because a cubic meter is, let's say you made a giant cube out of meter sticks. You took meter sticks, which are 3 feet or so, longer than 3 feet, and you made a cube out of those. That would be a fairly large amount of volume. And if you're trying to find the volume of just one rock, it would be a really small number in terms of cubic meters. But cubic centimeters, much smaller. A cubic centimeter is about the size of a sugar cube or a single dice. So a cubic centimeter is also appropriate. In the U.S., we are used to gallons for measuring volume. Sometimes we also use like cups and teaspoons and tablespoons, and there are actual like conversions between the three. Like I know there's 3 teaspoons in a tablespoon, and I think there's 3 tablespoons or so in a quarter cup. So it's really weird. And then there's like pints and quarts and gallons. So it gets really confusing. But in the metric system, it's really easy. It's just liters and then conversions based off of that. So it's really easy. We're not going to need this part too much, but 1 gallon, which is 3.78 liters, which is 0.00378 cubic meters. You're not going to need to know like how to convert liters to cubic meters in this class, but 1 gallon, like if you think of like a gallon of water or a gallon of milk, that's just shy of 4 liters, so 3.78 liters. All right. So when we're taking a volume of something, a lot of times we can take a volume of a liquid. So I'm going to talk about what these things are. These are called graduated cylinders, and sometimes you have really small ones and sometimes you have really big ones. The one on the left is a smaller one that has smaller numbers. That's to measure more precisely like how much liquid you have. If you have a much larger volume of liquid, you can see that the numbers are not going to be as precise going in between. So going from 10 to 20, if there's 5 lines in between, each one is going to be worth 2, right? So here's 10, here's 12, 14, 16, 18, 20. But over here, going from 1 to 2, each one is worth 0.2. So 1.2, 1.4, 1.6, 1.8, and finally 2. So this one's going to be way more precise when you're dealing with smaller volumes of liquid. And a larger graduated cylinder will give you measurements as well, but not as precise. You can also use a graduated cylinder not only for liquids, but you can actually measure the volume of a solid using a graduated cylinder. We'll talk more about that later, but basically it's measuring displacement, how you would throw an object in and the water level would rise. You can measure the difference between that and kind of get a volume there. Let's say we wanted to take a measurement of water. So let's say we poured water into a graduated cylinder and we take a look at it and we want to measure what this is right here. Well, this can be kind of confusing if you're kind of new to chemistry or you're new to measuring stuff in a cylinder, because water likes to hug the edges of a container. So when this happens, it can be kind of tricky. We've got two different options of measurements here. Like, where do I measure? Do I measure at the top of the water? If I do, I get 21.85. Or do I measure at the bottom of the water, which is 21.4? So the rule is that you would always measure at the center of your liquid. So that is called the meniscus. And the meniscus is right here at the bottom for water. Some other liquids, instead of curving down like this, they actually curve upwards like this. I know mercury, which is a metal, that's a liquid, does that. You would measure the top of it instead of the bottom. So always look at the middle of the graduated cylinder, kind of see where does the water line fall, and if it falls right there, that's where you're measuring. You're measuring the bottom of the meniscus. And in this case, 21.4 would be the correct measurement, and 21.85 would be incorrect. All right. If you have a perfect object like a cube or some kind of, cylinder or a rectangular prism, you could also just measure the sides, length times width times height. Probably something that you've covered in math class at some point. So volume is considered a derived unit because it can be calculated using length measurements. So length times width times height. In this case, if I take the length of this rectangular prism, which is 5, 1, 2, 3, 4, 5, multiplied by the width, 1, 2, 3, 5 times 3 is 15, and multiply that by the height, which is 1, 2, 3, 5 times 3 times 3 is 45. And since I had 5 meters and 3 meters and 3 meters, how many m's or how many meters do I have? Well, I multiplied it 3 times, m times m times m. That's where this 3 comes from. So that's where the meters cubed comes in. Okay, just probably a review for most of you. You've probably covered this at some point, or you're covering it in math right now. The final unit of measurement that we're going to talk about today is density. And density is actually one of the more important measurements that we're going to discuss today. And when I was a kid in school, I think in 2nd or 3rd grade or so, my teacher in science asked us, what's heavier, 100 pounds of bricks or 100 pounds of feathers? And it was kind of a trick question. Obviously, a lot of kids said bricks, but if you listen to the question closely, which one's heavier? They're both 100 pounds. Okay, so it was kind of a trick question. But if you think about density, which one would take up more space, 100 pounds of bricks or 100 pounds of feathers? And the correct answer to that is 100 pounds of feathers would take way more space than 100 pounds of bricks. And the reason for that is because of the density. And density is the mass per unit volume of a material. So on this picture, we have 3 different metals, but they appear to be the exact same volume. They appear to be the same size. So I could take the volume of that cylinder by taking the diameter, multiplying it by pi to get the surface area of this circle, and then multiplying it by the height to get the entire volume of that cylinder. But if I throw them on the scale, they have different weights. So we've got magnesium at 92, aluminum at 142, and tungsten, which is the densest material or the densest element on the periodic table, at 1,015 grams. So different weights, same shape. It's because of the density. How packed are those molecules? So if we're taking a look at magnesium, maybe the molecules are a little bit more spaced apart. In aluminum, maybe not so much. They're a little bit more compact. And then tungsten, those molecules are really, really tight, and you packed in a lot of material into that specific volume. So we're going to do a lab later this unit on density and kind of measuring density and realizing how density is a property of a material. It doesn't matter how much you have. The density is always going to be the same. I could have an entire block of aluminum, giant block of aluminum, and it would have the exact same density as this sample right here. Or even if you took like a sheet of aluminum foil, it would have the exact same density as an entire roll of aluminum foil. So density is a property of a material. The unit for density, there's a couple of different ones. There's kilograms per cubic meter. You could also convert that to grams per cubic centimeter. And because we're dealing with smaller amounts in this class, that's the one we're probably going to be using a lot, grams per cubic centimeter. And how do you calculate density? It's mass divided by volume. This is a very, very important formula. Definitely keep this in mind. Remember it, highlight it, put a star next to it in your notes or whatever. Density is equal to mass divided by volume. This is one of the very first formulas we're going to be using this year, and it's a very important one. So let's go ahead and do some density practice problems. We'll read this one together and then pause for a minute to kind of work on it and then solve it through. So the volume of a liquid that fills a flask is 750 cubic centimeters. The mass of this liquid is 525 grams. What is the liquid's density? And is it most likely to be water, gasoline, or ethanol? So take a minute or two and try to work this out. Put some data and numbers here, show your work here, and then write your answer here in the solution box. So go ahead and do that right now, and then we will pause. So you'll notice that there are 3 sections underneath this problem, one for data, one for work, and one for solution. I structure all of my problems like this because I think it's a very effective way of laying out all of your data, making sure that you're doing the work properly, and then finally coming up with a solution. Just being organized is a really great way to tackle some of these problems later on, especially once they get a little bit more complicated. This problem right here, not terribly complicated, so let's go ahead and jump right into it. The first thing we're going to do is we're going to find all of the numbers that pertain to us or are in the question. So the first number that I see here is going to be, let me go ahead and decrease the font size here first, 750 cubic centimeters. So I'm going to just go like that, cubic centimeters. Or actually what I can do is go like this. There we go. And the other number that I have is 525 grams. So now what I want to do is, once I've written down all of my numbers, I want to figure out what is the question asking for. So I look at the question and I say, what is the liquid's density? So the other thing we're going to write is density is equal to, well, we don't know yet, but we at least know what we're looking for. In the work section, we need to realize what was the thing that was given to us. What was the formula that was given to us to calculate for density? Well, if we remember, density is equal to mass divided by volume. All right, mass divided by volume. So going back to the data though, let's find out what each of these means. Like, what is cubic centimeters? What is that a unit of? Well, that is actually a unit of volume. So volume is equal to 750 cubic centimeters. And 525 grams, well, that's a unit of mass. Okay, so mass is equal to 525 grams. So to solve for density, abbreviated letter D here, we need mass and we need volume. So all we have to do is plug in the values for mass and volume to figure out what this is. So D in this case, density, is equal to 525 grams divided by 750 cubic centimeters. All right, let me go ahead and write that out. Cubic centimeters, like that. Okay, you plug that into a calculator and you'll get 525 divided by 750 gives me 0.7. D is equal to 0.7. But you can't stop here because you need the final unit in your answer here. So 0.7. And how would you calculate that? Well, you just take a look at the values that you're using here. 525 grams divided by cubic centimeters. So the answer is grams per cubic centimeter. Just like that. And that's actually the solution. So I'm going to go ahead and copy that over here, or just move it over here. And then the second part of the question is, what is that most likely to be? Is that water, gasoline, or ethanol? Well, taking a look at water, water is 1 gram per cubic centimeter, gas is 0.7, and ethanol is 0.79. So this is most likely to be gasoline. The next practice problem that we have says certain compounds called aerogels form rigid, lightweight foams that can support a mass many times greater than their own. If a sample of an aerogel has a volume of 87.3 cubic centimeters and a density of 0.25 grams cubic centimeters, what is its mass? So go ahead, pause, work on this, try to figure it out, talk to your table mates if you have to, but try your best, and we are going to pause here and work on it, and then work on it as a class. Okay, so we're going to start off this problem taking a look at the data, work, and solution sections. Starting with the data, we want to write down all of the numbers that we have in the problem. So the first number that we have here, I'm actually going to change to red ink so it can kind of differentiate between the problem and the work. 87.3 cubic centimeters. So what does 87.3 cubic centimeters represent? What is that a measurement of? That is a measurement of the volume. If you recall, for volume, that is one of the units that we could use. And the next number that we are given is 0.25 grams per cubic centimeter. All right, and what is that a measurement of? Well, the problem says that is a density, so I'm going to put the letter D here for density. And then the question is asking, what is the mass? So we don't know what the mass is, right? But we can figure that out. And in the work section, we're going to be using that same formula from before. Density is equal to mass divided by volume. But in this case, we kind of want to rearrange it so that we can solve for mass. So we want to leave mass by itself. And if I multiply both sides by volume, I get density times volume, so I'm going to put dV, is equal to mass divided by volume times volume. Okay, and so what happens there is that volume cancels out here and here. So these two volumes cancel out because we'll end up with one in the numerator and one in the denominator. So that cancels out there. And so if I rearrange this, it's going to equal mass is equal to density divided by volume. All right, I don't know why the format changed there. Let's go ahead and fix that. There we go. So we have mass is equal to density divided by volume, and we can plug these numbers in to figure that out. So let's go ahead and do that. Mass is equal to the density first, 0.25 grams per cubic centimeter. And I'm going to do something a little bit different here. I'm just going to draw a line here. All right, and then I'm going to put the volume in the denominator, 87.3 cubic centimeters. Can extend this out so it fits. There we go. And so what we'll see here is that we've got centimeters cubed in the numerator and centimeters cubed in the denominator. So unit-wise, that's going to cancel out. Centimeters cubed, cancel those out. We don't need them. So now we could just do the math, and we'll end up with a mass that is equal to, let me go ahead and put it in my calculator, 0.25 divided by 87.3. I get 0.04868, a whole bunch of numbers, but I'm going to just go ahead and round to 0.049. Okay, what is my final unit for this problem? Well, the only unit that I'm left with in the problem, I crossed out my centimeters cubed, I'm left with grams, and that's the only thing I have left. So grams, that's the answer for this problem. So now we're going to talk about this metric system that I've been mentioning throughout this entire lecture. Just to recall, the metric system is a simple universal way to measure based on the decimal system. And that's what's so appealing about the metric system, is that it's really easy to convert from one unit to another because it's multiples of 10. And it's very easy to multiply or divide by 10 in your head. All you have to do is basically move a decimal around. In the United States and two other countries, we actually don't use the metric system. We use what's called the imperial system. And to kind of give you an idea of how confusing it can be, if we're converting from feet or inches to feet, there's 12 inches in 1 foot. So that number 12 is the conversion factor. If we're going from feet to yards, it's 3 feet per yard. And so there's a conversion factor there of 3. And then if we're going from feet to miles, well, there's 5,280 feet per mile. So 3 different numbers that we have to memorize just to convert from different units of length. 3, 12, 5,280. And then it gets even more confusing when we try to convert stuff for volume, like teaspoons and tablespoons, pints, quarts, gallons, all that. It's not exactly clear-cut numbers every single time. So instead of having to memorize that, the rest of the world just uses a metric system where everything is just a conversion factor based off of 10. So it's very easy to remember and very easy to do the math in your head. So taking a look at some metric conversions, no matter what you're measuring, the metric units always have the same prefixes. All right, so a kilo of anything means that you have 1,000 of those things. So if I had a kilogram of something that I'm measuring, that means I have 1,000 grams. All right, the next one would be hecto. So if I had a hectogram, I would have 100 grams. If I had a decagram, that means I have 10 grams. The base unit just means I have 1, and an example of a base unit would be like a gram. A decigram would be 1/10 of a gram, a centigram would be 1/100th, and a milli would be 1/1000th. Okay, so for instance, the best way to visualize this is to take a meter stick. Now, probably somewhere in your science room, you have a meter stick lying around. Most science teachers have a meter stick lying around. And so the meter is going to be our base unit. And I'm going to pull up an image of a meter here. And this is kind of like a low-res image, but you can kind of still make out what it is. And you might notice that for every 10 numbers here, the number is actually bolded. So here's 10, 20, 30, 40, 50, 60, 70, 80, 90, and then there's no 100. It's just, it ends at the 100th centimeter. So what that means is that for every decimeter, or 1/10 of that meter, that number is bolded. So there are 10 decimeters in that 1 meter, because every decimeter is 1/10. Likewise, if you take a look at a meter stick up close, you can see that there's numbers, there's little tick marks over here. There's 100 of them, and I know that because a centi is 1/100th of a meter, and if I have 1 full meter, that means that I have 100 centimeters. If you think about like centi, for example, we've heard that prefix before. Like a century has 100 years. A dollar has 100 cents. A centipede has 100 legs. So that prefix centi means 100. And finally, just taking a look at this meter stick, if you find one in your science room, you can look at it. Every centimeter, if you look up really closely, there are 10 dashes in between these small numbers here. So if I take a look at any two numbers that are next to each other and count how many dashes there are exactly 10 dashes. And so how many dashes total are on this 1 meter? There's 1,000. And each dash is called a millimeter. All right? You can apply these prefixes to pretty much anything. So we were using the meter as our base unit, but you can have a millimeter, you can have a centimeter, a kilometer. We also do this a lot in with data storages. So now with computers and phones having more and more data, or if you have a data plan with your cell phone provider, you got to worry about how many gigabytes you're using every month or things like that. A long time ago, 25, 30 years ago, when people were still using computers and they were really low power, having like 1 to 2 gigabytes of storage on your computer, that was a big deal because files were in the sizes of kilobytes. But now, a simple photo can be a few megabytes, a video can easily be a gigabyte or 2. So dealing with larger quality videos and music and photos and things like that, they require more and more storage. So the prefixes might get bigger as time goes on. Right now, we're not really dealing so much with kilobytes as we are with megabytes and now gigabytes. And now you can get even tiny little SD cards that are terabytes, which are the next step. And if you're a big computer geek, after tera is a petabyte. And so what's the conversion factor here? In 1 gigabyte, there are 1,000 megabytes. And in 1 megabyte, there are 1,000 kilobytes. And so if you have 1,000 gigabytes, that's a terabyte. And if you have 1,000 terabytes, that's a petabyte, so on and so forth. Okay? So the metric units will either go up or go down by a factor of 10 when you're jumping from one to the next. So going from kilo to mega, yes, I mentioned that there's 1,000 of them, but 1,000 is a multiple of 10. So keep that in mind. So maybe we just jumped a few extra steps. But if we want to go from like 10 millimeters to a centimeter, 10 centimeters in a decimeter, and 10 decimeters in a meter, like we were talking about before, that's how we can see how the metric units go either up or down by a factor of 10. So when we convert, if you're really good at math, you can just do these multiplications of 10 either in a calculator or even in your head. But what I like to do for those of us that aren't really good at math is to use this step pattern. And so you might have this in your notes, and if you don't, you should definitely draw this out. But when we convert from one metric conversion to the next, we have to multiply or divide by 10 for every step. Okay? So if we go up the stairs in this picture, we have to divide by 10. And if we go down the stairs, we have to multiply by 10. So just remember that rule right now, and I'll do a quick practice problem here in a minute and showing you how we can apply this. So if we go up the stairs, we divide, and if we go down the stairs, we multiply. So that's the whole chart. If you have this again in your notes, go ahead and highlight it, put a star next to it. If you don't have it in your notes, quickly pause the video here just for a second, jot it down, and even write down these steps. Divide by 10 for every step, multiply by 10 for every step. So go ahead, jot this down if you don't have it. Moving forward though, we're going to talk about how we can convert these units. The main units can be scaled up or down using prefixes. So taking a look at these prefixes, the main ones, kilo, centi, milli. There are other ones like micro and nano. These are going to be like really, really small. And mega is going to be like up on the upper end. You will need to know some of these. I'm going to go back to this little chart here that we had earlier. And these are the ones you will need to know in order. Kilo, hecto, deca, base, deci, centi, milli. But there's a neat little trick that you can use to remember these. If you remember the phrase, King Henry died by drinking chocolate milk, that's like the common one that teachers use. I've heard it when I was a kid, and apparently it's still being used today. So that's the way I'm going to teach it, is that if you attribute the first letter of that phrase, King Henry died by drinking chocolate milk, you can correspond it to the different prefixes: kilo, hecto, deca, base, deci, centi, milli. All right? Here's some more prefixes and their abbreviations. You will need to know the abbreviations as well, going from kilo to milli. You don't really need to know micro or a mega or giga or anything like that. And then this one over here, this column or this row, that's for the base units. The main base units that we see are meter, gram, and liter, and those are their abbreviations. All right. Now we're going to move on to something called dimensional analysis, or some people call them bridge problems. And so what dimensional analysis is, it's a way of doing some type of math so that we can convert one of those units into another unit. So sometimes it's not really that easy to do the step method, and this is actually the way that I want to teach you how to do metric conversions. So for instance, if we have this problem that says how many millimeters are there in 2 meters, step 1 is to identify the initial and final units. The initial unit is meters. So how many millimeters are there in 2 meters? The initial unit that we have, what we're starting off in the beginning, is 2 meters. And final unit is millimeters. Okay, so before we do this dimensional analysis problem with the bridge method, we're actually going to take a look at it doing it this way. We have 2 meters and we want to convert it into millimeters. So where on these steps would you put 2 meters? Well, you would put it here on the base. Okay, so 2 meters goes here because the base units are, again, meters, grams, and liters. Those are the 3 base units. And if we want to go to milli, well, that's down here. How many steps do we have to go down to go from the base unit to milli? We have to go down 1, 2, 3 steps. Okay, and for every step we have to multiply by 10. Okay, and it's not going multiply by 10, multiply by 20, multiply by 30. It's not like that. It's like this. So we have start off with 2. 2 times 10 is 20 decimeters. 20 times 10 is 200 centimeters. And 200 centimeters times 10 is 2,000 millimeters. So we multiplied by 10 for every step. 10 times 10 times 10 for every step. So we ended up with a final number of 2,000 milliliters, but I'm going to show you a different way of doing it. If you know your conversion factor between meters and millimeters, you can write it as this, or like 1,000 millimeters is equal to 1 meter. And then step 3 is to multiply the initial quality by the conversion factor, and it's not as difficult as it may seem. So we're going to walk through it here as with a example. How many millimeters are there in 2 meters? You would set it up like this. First, start drawing your bridge. You have your line here. And then you're going to start off with the number that you already know. You know that you have 2 meters. Okay? Now you need to get rid of meters and you need to end up with millimeters. So pretend that meters is like in the numerator, and the only way to cancel out something in the numerator is to put something in the denominator as well. That's the same thing. So if I have meters in the numerator, let me put meters in the denominator. Okay? So meters in the numerator, meters in the denominator, they will eventually cancel out. but I'm going to put 1 meter here, and 1 meter is equal to, the other part of my conversion is 1,000 meters. And the key thing to remember here is that this conversion factor is equal to 1. 1,000 millimeters divided by 1 meter is 1, because 1,000 millimeters is 1 meter. So 1 meter divided by 1 meter is just simply 1. Okay? So you have 2 meters in the numerator. If you want to cancel it, you got to put meters on the bottom and then do millimeters on top. So meters cancels with meters, and you're left with millimeters. The final step is to multiply everything on the top, multiply everything on the bottom, and then do top divided by the bottom. So 2 times 1,000 is 2,000, and 1 is in the bottom here so that there's nothing to multiply it by. So 2,000 divided by 1 is simply 2,000. So that's our final answer here, 2,000 millimeters. Let's do one more problem here. How many centimeters are there in 2.5 kilometers? Again, you can use that stair method if you'd like, but I'm going to show you how to do it with the bridge problem. So we're going to set it up like this. 2.5 kilometers is our initial number, and that's going to go like in the numerator part. And then we're going to have our conversion factor. Now, I don't necessarily have a conversion factor between kilometers and centimeters, but I do have a conversion factor between kilometers and meters, and another conversion factor between meters and centimeters, which are even smaller. So how many meters are there in 1 kilometer? If you run cross country or have ever run a race, you know that like a 5K is 5,000 meters. So 1K would be 1,000 meters. So 1 kilometer is equal to 1,000 meters. And if I want to cancel out kilometers and put meters, I'm going to put kilometers here on the bottom. Numerator has kilometers, denominator has kilometers, and I'm going to convert that to 1,000 meters. All right? However, meters is not my final unit, so I got to keep going with conversion factors. And now I know that I can convert the meters into centimeters by writing another conversion factor. So you want to convert to your base unit first. Kilometers cancel out with kilometers. And here's my other conversion factor. So we're building a bridge. We're kind of going along, adding conversion factors until the entire bridge is built. We have meters on top, meters on bottom, and 1 meter is equal to 100 centimeters, so that's my conversion factor. Meters cancels with meters, and I'm left with my final unit as centimeters. Now what I'm going to do is multiply the top, multiply the bottom, top divided by bottom. So when I do this math in the calculator, I'm going to do 2.5 times 1,000 times 100, set that number aside. Then I do the bottom, 1 times 1, set that number aside. Top divided by bottom, you end up with 250,000 centimeters in 2.5 kilometers. Now the key thing that I want to mention from before is that it's very important to pick your units when describing a distance. If you run cross country, for instance, everyone running in the fall right now, if your coach tells you, hey, I want you to go run 2.5 kilometers, you kind of have an idea of how far that is. But if your cross country coach told you, I want you to go out and run 250,000 centimeters, even though that's the same distance, it's much harder to picture that in your head. So picking the right unit in terms of context of a conversation is very important. So keep that in mind as well. All right. Now I'd like for you to take a look at practice problem number 3 and go ahead and work on that. Practice problem number 3 says, Carol says the distance from her house to the nearest movie theater is 7,920 feet. What is this distance in miles, and what is this distance in inches? So now we're discussing our dimensional analysis problems and converting from one unit to a next unit, both measuring the same type of measurement. These are both measuring length, or in this case we have 3 different things for length. We've got feet, miles, and inches. So this is where it becomes appropriate to kind of know and distinguish what unit you're using to describe your measurement. In this case, it's really hard to picture what 7,920 feet looks like, but you can kind of gauge that in terms of miles. So let's go ahead and start this problem off just like we start off any other one. We're going to write down the only number that we have, 7,920 feet. Okay? And that is my length, but we don't really need to write that down. We also need how many miles is that? Or let's write it a little bit different. Feet to miles. So we need to convert feet to miles. And then we need to convert feet to inches. Okay, so let's go ahead and split this off into two different work areas. I'm going to go right here, split it down in the first part. The first question is, how many miles is that? Well, let's go ahead and start off our bridge problem, 7,920 feet. And I'm going to go ahead and just draw my bridge here. And I want to convert that into miles. And so, do I know the conversion factor between feet and miles? Well, I personally do, because I learned it when I was in school. Not a lot of students are taught this anymore, but going from feet to miles, I need to know how many feet are in 1 mile. I know that the conversion factor, I'm going to write it here, 1 mile is equal to 5,280 feet. Okay? The other conversion factor I'll need later is that 1 foot is equal to 12 inches. Okay? So I'll need both of those later. So this conversion factor, I have to put it right here in this spot, but I need to make sure that I am canceling out the unit that I don't want and leaving the unit that I do want. So to cancel out feet in the numerator, I have to put feet in the denominator. So that's why I'm going to put 5,280 feet in the denominator and just put the other one in the numerator, 1 mile up here. Okay? And the last step is to just double check my unit here. Do feet cancel with feet? They do. And then I'm left with the last unit that I want, which is miles. Multiply everything on the top, multiply everything on the bottom, and then do top divided by bottom. Okay, so 7,920 times 1 is just 7,920. And then 5,280 by itself. And that is going to give me an answer of 5,280. 1.54 miles is what you should have gotten here. So I'm going to go ahead and put that in a new spot. 1.55 miles if we round correctly. Okay? So the second part of the question is, what is this distance in inches? I'm going to go ahead and start off my bridge problem like before. I'm going to write down my number that I'm starting with, 7,920 feet. Let's go ahead and draw in a bridge here and put in the conversion factor. So the conversion factor again is 1 foot is equal to 12 inches. I want to get rid of feet and leave it in inches. So I'm going to put 1 foot is equal to 12 inches. Okay? Double check that my units cancel and I'm left over with whatever I want. I have feet cancel with feet, and that's good. And in this case, I multiply the top, multiply the bottom, do top divided by bottom. So 7,920 times 12 divided by 1. But I don't really need to write that. If you understand that dividing by 1 will just give you the same answer, I can just leave it as 7,920 times 12, and that gives me an answer of 95,040 inches. Okay, so those are my two answers, 1.55 miles and 95,040 inches. All right, hopefully that was enough help for you to kind of get you started with bridge problems and converting the metric units. What I'd like for you to do now in class, and if you don't finish, you can do it for homework, is practice problems 4, 5, 6, 7, 8, and 9. So there's quite a few here. Go ahead and work on those for the remainder of class, and when everyone is done, we will go over these. And there's a video, like I mentioned in the beginning of the lecture, there's a video on these practice problems and how to complete them.